This seems like an easy job.
Oh yeah. Just wake up in the morning, double performance, no problem.
Right. Hey Juan, we have a fun engineering discussion for you today. I am joined by Tom Petersen from Intel. And the last time we talked, it was about GPU busy and presentmon.
Yes.
And so today we're going to do a technical kind of engineering discussion on drivers. So Tom was coming out here. We're going to have, I think it's going to be maybe 3 total videos we're doing.
I hope so.
All of them deep dives on different topics. And this one, the question I had at a top level was like, what are drivers? What really do they do?
Yeah.
And you start drilling down into it all the time. And especially with Arc, we're seeing driver rollouts that are
lots of drivers.
And it's game specific. This game improved by X%.
Yep.
So the question I wanted to get into today, and I will be learning with you all, is what does that mean?
That is an excellent question. And I totally agree. And thanks for having us out.
Yeah.
I always love talking to you guys. It's always great getting back to Raleigh. But it's a tough question, right? Because there's a lot to unpack. So I drew a slide, of course,
okay,
right?
Yeah.
And this is the entire software stack. So I thought what we'd do is walk through it and then answer a couple questions about how do we improve performance.
This in-depth technical review is brought to you by us and store.gamersnexus.net. We don't take money for these discussions and interviews in order to maintain control over the content and independence in reporting. To support our ongoing efforts to seek experts, engineers, and technicians and bring them out for discussions about technology, head over to the store and grab one of our items. The GN15 Metal Emblem Pint Glass has been wildly popular since launch, and it's in stock and shipping now, featuring a custom-made metal GN badge that's shaped to the glass. We hand assemble these in our East Coast warehouse in the US. If you like home bar supplies, you might also like our Bar Runner bar mats that serve as great stands for drying and feature 3D PC components in the mat. Finally, our coaster packs can complete the set and give you a pack of 4 individually designed coasters with PC hardware theming. Learn more at store.gamersnexus.net.
Okay, so starting at the very top, that would be a game like Half-Life or Fortnite, whatever. And what the games do is they have like something called game state, which is like there's an AI over here, there's a box over there. It does all of the logic related to running the game, but it also does something called a software renderer. And the software renderer is like, I want to draw a picture of my game state. How do I do it? Well, it uses an API called DirectX, right? So DirectX or Vulkan are the APIs that the games use. And what that's all about is saying, in the game itself, it's created things like meshes and geometry and textures, and it's trying now to communicate that all the way down into this massive software and hardware complex so that you can get a picture drawn. Yeah,
and I think, so when we talked about this one a little bit before starting, sorry to break the illusion, but I try to know a little bit of what we're going to talk about. So the question I had right away was, is this kind of canonical or hierarchical in terms of execution, where does it go from here to here to here to here?
It does.
And can anything skip a step or not?
It generally doesn't skip because the language that games speak is DirectX. And DirectX talks to the D3D runtime, which is also a Windows thing running on the operating system. And that is what talks to our driver stack. And the driver stack, the UMD is a user mode driver. That talks to the KMD, which is a kernel mode driver. And eventually that interfaces to our hardware.
Is this sort of the same for everybody? Is NVIDIA and AMD, it's the same?
Yeah, I couldn't find a Microsoft picture of this, but if I had, it would have been exactly the same.
Okay.
Yeah,
so, because ultimately, I guess what I was trying to tackle with this is, we hear all the time about driver optimizations. Another common phrase that gets thrown around is like, this game is unoptimized.
Yes.
I don't think I've ever heard anyone say this game is optimized.
Yeah, that's a common problem. Yeah, no question.
Pretty rare to hear it be specifically optimized, but that all falls into the same, how does this all work?
How does it all work, yeah. But I think the easiest way to think about it is this guy knows about game state and things that are very large and logical, and he's now converted it into DirectX primitives.
Or Vulkan, I guess.
Or Vulkan, yeah. Things like, here's some vertices, here's a shader. The shader is a critical part of this because that's actually a program that is written by game developers or game engine developers, and that describes how am I going to color a particular pixel.
Okay.
Right, so that shader is written in text, believe it or not.
So this is an important building block, I think, shaders specifically.
Yeah.
And there's you also hear the word shader thrown around as a descriptor for the physical hardware of a CUDA core stream processor.
Yep, they're all shaders, yeah.
Yeah.
It's an overused term. In this case, shader in the DX sense refers to the program that represents the sequence of operations that you would want to use to color a particular pixel or any other operation, really. But what happens is that shader gets communicated down through this runtime and eventually lands in a call to the UMD. And this is where the first time that the whole software stack knows, hey, I'm Intel, and I'm going to use the Intel software, and I know what hardware I'm targeting, so I can start to take this sort of hardware-independent sequence of calls and start targeting it at the hardware that's in the machine. So one of the big things that happens inside the UMD is called shader compilation. So there's a giant compiler that's sort of built into our driver that takes that text file and generates a series of instructions that will actually run on our GPU.
Right.
So that's a big part of the magic.
Is that different or related at all to when you see a video game, say, compiling shaders?
It is exactly that.
Okay.
So when you load a shader, you're going to read a bunch of stuff from memory, and then you're going to run a long process that's optimizing that shader. And if you do a whole bunch of shaders, it can cause a long delay. So some games do that all up front so that you don't have to do it dynamically. Because if you don't do it up front, every time you load a shader in your application, you'll see a hitch in the rendering pipeline. And today, most people don't like that. They want to push all that stuff up front. And of course, we're now caching all those results. And shader compilation is an art in itself. And there's much optimization left to be done there.
Okay. So are the shaders out of your hands on the driver side, or I mean, you kind of, there's a little bit of an asterisk
there. Yes and
there,
no, right? Yes and no. So the artwork that is described in the shader, like what color pixel do I want, is depending on the lighting and the materials and all that kind of stuff. That's all in the game and in the engine. But when we get the shader, it's our job to convert that into efficient instructions. And a lot of times that's, just take the shader, compile it, and it's all good. But sometimes that shader is just written in a way that's less optimal for our hardware, in which case we can actually replace that shader with a functional equivalent one that works better in our compiler.
So is that when any of the three GPU manufacturers talk about optimizing, it's replacing code?
Well, that's one of the, there's lots of tricks and trades that we do, but all of them happen in the UMD. Things like the UMD is responsible for memory management. It does threading. It does effectively sort of like memory allocation, deallocation, and reallocation. And it also does sort of talking down to the kernel. So you can think of it, in the UMD, there's just a lot of opportunity to do interesting things.
Okay, so I guess the start of our story here is you have shader, some program execution going through the API. We hit the runtime hands it off to UMD.
Yep.
And then what do you want to talk about in this block?
Well, the UMD, again, is responsible for most of the optimizations. And there's one UMD effectively per different type of API, so DX9, DX11, DX12, Vulkan.
Right.
But again, think of it as like doing the heavy lifting for like SIMD allocation or working with register allocation and deallocation. And that's, again, where we're going to see a lot of our tricks. Once all that's loaded up, it has to start talking to our hardware, and that's where KMD comes in. KMD is responsible for doing kernel mode driver, and it's doing things like scheduling the hardware. If it's doing a software scheduler, it can do more things like more memory and management. It'll also do power and clocking and fan, all a bunch of stuff.
I mentioned this earlier, but I think maybe helpful for everyone. My primary association with the word kernel in general is Linux. Compiling a Linux kernel as a fun and enjoyable pastime.
It is.
Can you explain to me what is a kernel? Or what is its use here?
Yeah, well, the kernel is think of it as like the lowest seed of the operating system, and it's protected. So it's the only piece of software that's allowed to access registers of the graphics cards or registers of the system, and that's intentional because sometimes you get misbehaving applications that crash, or you get malevolent applications that are trying to hack things. So this is effectively an architected protection mechanism where you can only talk to like the lowest hardware things through specific APIs. Right? So you can't just like start tweaking a register anymore. that register tweak has to go through an architected API, which provides some form of security.
Okay, so it's kind of, is it, I guess, filtering between everything above it and the graphics firmware?
Yeah, think of it as the KMD has very, well regimented ways of being talked to, and the KMD knows all about the graphics firmware.
Okay.
Right, so that's the relationship. The firmware obviously is very specific to a card, and so this whole stack is effectively translating from a game that knows absolutely nothing about the hardware to very, very specific micro optimizations.
Okay.
So the graphics firmware is another big chunk of code. It's doing things that are more real time. So if you're looking at like, what's my clocking algorithm? When do I change P states? When do I ramp fan, lower fan? All of that's happening in the graphics firmware. And it knows all about all the registers inside of our GPU, and it's sort of manipulating that. So if you do overclocking, most of that is done in the graphics firmware, talking up through these steps.
Okay, I see. Yeah. And then we get to hardware.
Of course, the hardware.
When drivers are communicating with hardware, how targeted does that get? I mean, is it saying, I need to send this specific task to this specific physical piece of hardware on the silicon?
Yep.
Is it broader level?
Yeah, the way to think about it is on GPUs, it's basically a command buffer structure. And what that means is there's pointers inside the GPU that are pointing at GPU memory, and it's going to look there to find a series of instructions. And then inside the GPU, there's a little bit of dispatch logic that reads those instructions and then kind of spreads it around across the GPU. But a lot of that scheduling is actually done in the UMD, where they create that instruction sequence and put it in that buffer. And then the GPU is basically going out to find that buffer and then scan through those instructions to spread it around the units of the GPU.
I see. I think this is going to progress us to the next slide.
Yes.
But my question is, but what does it mean when you're going to optimize?
That's an excellent question. Excellent question. Well, optimization, I said, mostly happens inside the UMD. And that's the place where you have more flexibility. You have the compiler. You know what your hardware is, so you can kind of tweak things. So I think it's easiest to talk about it with an example.
Yeah.
Okay, so first of all, shout out to Hugo LaMarche. Longtime fan of the show, got these traces for me in very, very quick time.
This is an engineer at Intel,
This is one of the application engineers at Intel, works with ISVs, so I really appreciate it. But what this is showing you is something called Pix, which is a Microsoft tool. And on the top, it's showing a game before, and on the bottom is after. So we're in the process of optimizing this title.
Let's define some of the scales, too, to make it a little easier to interpret. So this is time
in milliseconds.
Yeah.
This is sort of like activity that's happening on the CPU side. This, the white bar, I believe, white bar is a vector engine sort of utilization, and blue is more of a like activity on the GPU, right?
And then these things, as we see them, are these bits of...
These are like different phases of what's happening inside. This is one frame. So in one frame, you're going to go through a sequence of phases on the CPU side that are effectively, the process of generating an image. And down here, it's showing the impact on the GPU, what's actually happening in vectors and matrices and otherwise utilization. So the idea is the shorter the better. Right?
So this is a troubleshooting step to identify.
This is a troubleshooting step, right? And this is you can see it's very complicated. And you're doing this per frame because you're trying to say, how do I make this game better? Right. So what this engineer did is and by the way, this is a work in process. This is not a done thing. Right. So it started off long, and they identified this one section over here where they saw an opportunity. So I'm going to blow in over there.
Yeah.
So it's that same section. And looking at it a little closer, you can see effectively they were not satisfied with the sort of the vector utilization, right, with the activity on the vector engine. And so they figured out we can use a technique that we use where effectively allows more registers to be available to that process. And they were able to basically improve the vector throughput by about 30%. Right, so that shortens up the time, and that's an optimization. In this specific case, the problem is that they're swapping out registers. So this particular thread is using too many registers, causes a register spill. That means that the execution engine is idle a lot. So effectively, by making more registers available, you can keep that spill down.
So basically, in this instance, an underutilization problem of a specific piece of hardware.
Yeah, well, the vector engine, right?
Yeah.
The vector engine up here is sadly like half utilized.
Yeah, it's interesting because we've kind of told this story with ARC specifically over the last, I don't know if it's been 2 years almost.
It's been a journey.
Yeah, but we've told this story where I think you see the improvement that comes from a driver update.
Yeah.
and it sort of helps to differentiate that the hardware can be more powerful than is necessarily being leveraged.
Yes, and that's still the case today.
Yeah.
So think of it as the hardware that we built is very, very capable hardware. You know how big the die is and that it's a high performance engine. And it's still got headroom to be unlocked. And this is all a part of optimizations that you got to look at hundreds of games. And so for us, having our high performance engine, it's opened our eyes to things that need to be
So
fixed.
this to me seems insane to try and scale.
Yeah.
Because if you do this per game and you're trying to identify bits and pieces you can improve.
Yeah. How does that scale?
Yeah, is there a way to scale it?
There is, because fortunately most games are built on engines. And so engines have similar patterns. And so this particular optimization will work for all games that has the same engine.
I see.
Right, and so you identify the sort of like the inheritance of engines in games, and you can prioritize that work a little
So when
bit.
you start work on, like say when ARC was prepping for launch or something, how do you define what to target? Because you can't just say prioritize everything. There's
No.
a million games.
Yeah.
So how do you
do
that? Yeah.
Well, it's hard, right? And we start with obviously looking at reviewers and seeing what are reviewers focused on, because you guys are representing what your community. We've got giant spreadsheets of every game that's used in the press. Then we also go look at Steam surveys. We look at top title lists.
Right.
And again, it's all also important about what's new that's coming, because we have to have a driver ready when the game comes out,
Right.
which means our engagement has to start long ago. And you can look at the type of work that we have to do. We have to get builds months ahead so that we can improve the driver so that it's ready when the game launches.
That makes sense. Yeah.
This is what we call our day zero driver effort.
So we've really only talked about like 2 lines here.
Yeah. There's a lot more going on
That's
here.
what I was going to ask. So what are the other types of checkboxes you might be able to enable to show something here?
Oh, like if you're, let's say you were an engineer and trying to optimize this?
Yeah, I mean, do you look at cache utilization or something like that?
Yeah, you
like,
would look at memory capacity. You would look at like memory, like there's another tool that we have called GPA, which is our graphics performance analyzer. It's available. Anybody can download it. It gives you histograms of hotspots. It's a very cool tool. So that'll kind of guide you into the area that's worth fixing. And it looks at things like register utilization, bandwidths on different types of interfaces. And you can usually kind of dial it into, I'm completely saturated on one interface, can I do anything, you know?
When you have a shader that's either pre-compiled or that executes on the GPU at some point, is that a transient thing that's stored into volatile memory? Or like, do you have to keep cycling through every time you encounter that?
The way DirectX works is the first time you encounter a shader, there'll be a call to compile it. And once it's compiled, it lives as a binary blob. And it doesn't disappear unless the application throws it away intentionally.
Okay.
So those will, as you launch a game and compile a shader once, it's done with compiling.
So does that binary live in memory?
In memory, GPU memory.
Okay.
Yeah, now the interesting thing is, there's technology that's evolved since the beginning of time where now those blobs can actually be saved and reused across runs of the game. So that's called shader caching. And that happens now on our driver as well.
Okay. And does that end up living in actual system storage somewhere?
Yeah, that lives on a disk. And effectively that'll get loaded in rather than recompiling.
I see. Is this an Intel thing, a Microsoft thing? Yeah, there's one that was like shadow depths, render virtual shadow maps.
Yeah, that's all coming out of the game.
I see Nanite, so I guess this is Unreal Engine.
Yes.
Okay.
So this is all coming out of the game engine or the game developer. And it's words that they're using inside of their code.
I see.
Yeah.
Okay. This seems like an easy job.
For them or for us?
For you guys.
Oh yeah. Just wake up in the morning, double performance, no problem.
Right.
But I do appreciate all the work that the engineering team. Now you can kind of get a sense of what has this year been like. It's been a lot of this and bigger things, right? We've talked about re-architecting the driver. You now know what are we talking about, right? You're like opening the hood and replacing the guts of the whole thing. It's big.
Yeah.
But the progress has been pretty impressive.
If we go back to your first image,
Sure.
Has Intel completely switched off of, was it DirectX 9 on 12?
There was something we did originally called 9 on 12, which was a Microsoft layer. We're not using that anymore.
Was that in here,
Yeah,
in the middle?
it's roughly right at the top of this. It would have been a layer that's sort of like above the UMD driver.
It's like a translation or
Well, it
something?
was a driver, right?
Oh,
It was a
okay.
DX9 looking UMD driver, and it would talk to our DX12 UMD driver. Yeah, we switched completely off of that. We're on our new modern driver architecture for DX9, DX11. We're continuing work on both the 11 as we go forward. More and more titles are going to move to that driver. So it's all
Yeah, so that's most of the stuff we've covered is pretty agnostic to all GPU vendors. On the ARC specific side, I think one of the things I mentioned we did a hardware news update after we talked following the ARC revisit, and I mentioned we had talked about you had a specific phrase where you're like, we're getting ready to flip the switch on DX11.
Yes.
So that I didn't feel confident enough in my understanding of what you were talking about to try and explain it to the audience.
Yes.
So can you explain to me what
that means?
Yeah.
So we have two driver architectures for DX11 right now. We have kind of our old legacy style, and we have our new one, which is higher performance. But we want to make sure that as we move titles from the old to the new, that everything works great. So we're actually testing and profiling every title and then putting it into this sort of white list that can use the new driver.
Okay.
So that's what's happening. We just had a big driver release that came out, I think, the week before last, added like another 40 titles. So it's a progress. It's going to continue to happen, but we're most of the way done.
So what really is being switched, though? Like, I mean, you talk about re-architecting, I guess.
Yeah. So imagine that we have two of these guys. So there's one that has a more of a legacy style of doing DX11, and one that is much more modern, re-architected, using all the learnings over the last year.
Okay, I see.
And so just which path does a game take?
Okay, so you basically, you take what you've encountered since launch, and then is this one of those situations where it's more effective or more efficient to build from the ground up, I guess, and replace rather than...
The whole driver team has really taken the challenge, and you can imagine the kind of pressure that they were under over the last year, and it's really dramatically turned around. So Alex and Andrew's team both done an amazing job.
I have one more I want to ask, and we'll try to do this without getting you in trouble with
You can't get me in trouble.
So for game optimization, I've said this on camera before, but we hesitate to throw around terms like a game is unoptimized. There's a few specific examples I can think of, and for Tom's sake, I won't say.
Oh my God.
But there's a few specific examples. By and large, though, I don't really feel comfortable saying this game is unoptimized because I don't really know what's fair to expect. But from a driver development level, if we look back, well, I guess actually even either one of these works.
Okay, back here?
Yeah.
You can tell. You can tell.
Yeah. So, what does that mean to you if someone says, if someone you trust, like an AE, an application engineer, says this is unoptimized, we need to try and help them.
Yes.
Right. What does that really mean? What does that come down to?
Sometimes changes have to be made on the application side. There's no question about that. But sometimes we can do our part, right? And that's the stuff that we were talking about now. So normally I'm more thinking, or we're more thinking about what can we do. But sometimes it's how do we help the third party?
Right.
And that's a harder thing to do because they've got a whole bunch of other priorities going on, and they've probably got a software architect that brought them to the place that they are. So getting change into like a fundamental framework is very difficult.
Yeah, I guess a lot of that probably happens at the engine level too.
A lot of it happens at the engine level. Yeah. Games get coded at different levels depending on which company you're at, but a lot of people are now using game engines, and so really for us, optimize the game engines is really key. Really.
Are there any common misconceptions you see about drivers that you want to try and talk about?
Maybe the thing that I would clear up is that there's it is essential, right? It does the heavy lifting of targeting very neutral sort of multi-vendor code to our hardware, and it's our solution is a hardware-software solution, and the hardware, while elegant and does math really well, is mostly dumb, right? It's intentionally mostly dumb, and all of the like wicked algorithmic stuff is mostly happening in the driver.
Yeah, that makes sense. I have a software developer friend who is biased by nature of being a software developer to say that software development is the hardest part. But,
I'm a bi. I speak both languages, and I would tell you that I don't know. Bits. I would just call it typing. Software is just don't take this. I love software, but hardware. That's where my heart is.
Right. Well, yeah, I appreciate the walkthrough.
Yeah.
Hopefully that helps. If for anyone in the audience who has just broad or specific questions about topics like this, post them because I do actually read them. And next time Tom's out,
Yeah, well, awesome.
we can do the same thing.
And please correct anything I said that's a lie. I'd love to see it. Fire me up in the chat.
I'm looking forward to someone really psychoanalyzing
this
your color choice.
D3D runtime.
Yeah, that's right. Well, I think that's it for this one. We'll have two more. We have one on media, so things like encode, decode.
Yep.
And then we have one on PresentMon.
I'm excited about that.
Yeah. So check back for those, or maybe they're up already. I don't know. And Tom, thank you for watching.
Great to see you again.
We'll see you all next time.